Assalamualaikum warahmatullahi wabarakatuh, madam. My name is Mohd and Hakeem bin Umar. I'm from Group C and I will be presenting our assignment question 1 design simulation, which is 3-bit single input to parallel output shift register SIPO. Okay, in our design, we use a D flip-flop to store the serial data as it shifts through the register. Then we connect the output of the first flip-flop to the input of the second flip-flop and the output of the second flip-flop to the input of the third flip-flop to create a serial input connection between the flip-flop. And then we use a key switch as the data input, which is then ANDed with the output of the third flip-flop, which is Q2 bar, to control the parallel output of the flip-flop. And as for the clock signal input, we use a digital clock generator and set its frequency to 200 Hz to make sure the shifting process can be seen clearly. And finally, we connect a probe onto each output of the flip-flop to see the data movement. Okay, now let's start the simulation. Okay, right here, you can see the data movement of our shift register. You can see that the data is being shifted from Q0 to Q1 and then to Q2. Alright, let's look at the timing diagram of our input and output. Okay, right here, this is the timing diagram for our clock signal, and this is the timing diagram for our input signal. And this, the green one, is the output of the Q0. The blue timing diagram is the output of the Q1, and the red timing diagram is the output of the Q2. Okay, right here, we can see when the data input is 0, the output of Q0, Q2, and Q3 is also 0. Then, when there's an input from the data input, we can see that the output is being shifted from Q0 to Q2 and Q3. Okay, I think that's all for our question 1 design, and we'll be moving to our question 2 presentation. Thank you.
Okay, for this part, I'm going to explain about the question 2, which is verilog code. Before we go into the verilog code, this question asks to design verilog code to convert 4 bits input value into its equivalent 0 to 9 value. But we only assume that the output will be displayed by 10 LEDs, which is L0 until L9. This is the functional block of the question 2 module. Before we go into the verilog code, I would like to show the truth table of this module. As we can see here, for input 0, which is the binary is 0, 0, 0, 0, the only LED is turned on is LED 0, which is this is 1, and then the other is turned off. For 1, which is 0, 0, 0, 1, LED 1 will be turned on, and so on until LED 9. So next we move into the verilog code. This is the design of verilog code, which is first we name the module and the input, which with the output. The input is 4-bit binary, and the output is 9 LEDs. In this verilog code, we use behavioral modeling style. So in this case, if B, which is binary input, is equal to 0, 0, 0, 0, the L, which is LED, will turn on. The output is 0, 0, 0, 0, 1. So same as the others until LED 9. We set the input other than 9 input here will be default by 0, which means all LED will be turned off. As for the test bench, we will monitor the time, binary input, and the LED. So we start with the functionality of this module. First, we test with 0, and then 1, 2, 3, 4, 5 until 9, and then we will stop. Then I create this dump file BCD to show the AP wave. After that, we choose the simulator, which is Aldec Rivera, and then open AP wave. After that, we run the code. and the AP wave will be shown like here. So this is the output for this module, but this is in hex up. So we change it into binary, so we can validate either is correct based on the truth table that we got earlier. So as we can see, the first input is 0, and the LED that will turn on is LED 1. The first one, LED 0, which is 2 power of 0 equal to 1. Then the next one, after 10 millisecond, it will input the second input, which is 1, and second LED will turn on. It will continue until LED 9. That's all from me. Thank you.